Hello. Now we're going to compare Mealy machines, more machines, and different types of LLMs with our friend Gemini. Gemini 2.5 Pro. Alright, we have an answer. Let us listen.
Okay, let's compare Mealy Machines, more comparison between Mealy Machines, more machines, and large language models LLMs, breaking it down again. As of today, April 14th, 2025, these represent different approaches to computation and processing information. Part 1. Finite state machines, Mealy and more. Think of finite state machines, FSMs, as simple machines that can only be in a limited number of specific conditions or states at any one time. They follow exact rules to switch between these states based on the input they receive. 1. Mealy machine core idea. The output it produces depends on two things: the state it's currently in and the input it just received. Analogy. Imagine a basic vending machine. If you are in the state ready and you insert a coin, input, the machine might immediately output coin accepted during the transition to the has coin state. The output happens based on the combination of state and input. Key trait outputs are tied to the transitions between states. 2. More machine core idea. The output it produces depends only on the state it's currently in. The input doesn't directly affect the immediate output, only which state comes next. Analogy. Think of an elevator's floor indicator light. The light shows 3, output, simply because the elevator is at the 3rd floor, state. The button you pressed earlier, input, caused it to go to the 3rd floor, but the display only cares about the current state. Key trait. Outputs are tied directly to the states themselves. Quick comparison. Mealy versus more. Feature. Mealy machine. More machine. Output source. Current state plus current input. Current state only. Output timing. Changes with transition. Changes when state is reached. Of states. Often fewer. Often more. Part 2. Large language models, LLMs. LLMs are a completely different beast. They are a type of artificial intelligence, AI, built using complex structures called neural networks. Core idea. LLMs are trained on enormous amounts of text data, like books, websites, articles. They learn grammar, context, facts, reasoning abilities, and how to predict the most likely next word or piece of a word in a sequence. They don't have simple, predefined states like FSMs. Analogy. Think of an incredibly well-read and articulate assistant. You give it a prompt or question, input, and it uses its vast learned knowledge to generate a relevant and coherent response, output, constructing it word by word based on probability and context. Common types of LLMs, simplified by function. 1. Text generators, e.g. GPT-4, Claude 3, primarily designed to create new text based on a prompt. They predict sequences of words to generate articles, emails, stories, code, etc. Example use, writing a draft email based on a few bullet points. 2. Text understanders, e.g. BERT, optimized to analyze and understand the meaning and context within a given piece of text. Example use, determining if a customer review is positive or negative, sentiment analysis. 3. Text transformers, e.g. T5, BART, designed to convert text from one format or structure to another. Example use, translating text from English to French, or summarizing a long document into a short paragraph. Part 3. Key differences, FSMs versus LLMs. Feature, FSMs, Mealy/more, large language models, LLMs. Nature, simple, rule-based automata, complex, data-driven AI, neural networks. Operation, follows explicit, predefined rules, uses learned patterns and probability, memory, limited to its current defined state, vast knowledge encoded in model parameters, complexity, low, finite small number of states, extremely high, billions of parameters, predictability, highly predictable, deterministic, probabilistic, can be creative/unpredictable, purpose, control logic, parsing simple data, understanding and generating human language. In summary, Mealy and Moore machines are simple, predictable models excellent for tasks with clearly defined states and transitions, like controlling hardware or simple software logic. LLMs are vastly complex AI models, trained to handle the ambiguity, nuance, and creativity of human language, operating on learned patterns and probability rather than fixed rules. They serve fundamentally different purposes in the world of computation.
Let's do some follow-up questions. More machine of is the processing step, should I say? For LLMs, where so out, okay, let's see.
That's an interesting thought. Theoretically, yes, you could use a Moore machine or any FSM concept as a pre-processing step for an LLM, but in practice, it's generally not common or particularly useful for typical LLM tasks involving natural language, mainly due to a fundamental mismatch in complexity and purpose. Here's a breakdown of why and where it might rarely apply. Why it's generally not used. 1. Complexity mismatch. Moore machines operate on a finite set of states and recognize patterns defined by strict, simple rules, often equivalent to regular expressions. Natural language is incredibly complex, ambiguous, context-dependent, and far beyond what a simple FSM can effectively parse or represent. 2. Information loss. An FSM processes input symbol by symbol and transitions between states, representing a rich text input solely by the final state or sequence of states of an FSM would discard vast amounts of semantic and contextual information that is crucial for an LLM to understand the input properly. 3. LLMs are powerful sequence processors. Modern LLMs, especially those based on transformer architectures, are inherently designed to process sequences and capture complex dependencies and structures within the text without needing a separate FSM preprocessor. Their internal mechanisms, like attention, handle context much more effectively. 4. Standard preprocessing is different. LLM preprocessing typically involves tokenization, breaking text into words or subwords, and converting these tokens into numerical embeddings. This process retains much more information about the sequence and semantics than an FSM state transition process would. Potential niche scenarios where the concept might apply. Despite the general limitations, one could imagine highly specific, constrained scenarios. 1. Input validation for rigid formats. If you expect user input in an extremely strict, simple format before it's interpreted more broadly by an LLM, an FSM could validate this format. For example, checking if a command follows a pattern like action parameter before sending it to the LLM. The FSM state could indicate valid format or invalid format. 2.
Okay, I
Simple
get
state
it.
tracking for structured data. If the input to the LLM isn't free-form text, but rather a stream of data with very simple, predictable modes, an FSM could track the current mode. For instance, processing a log file where lines represent different types, e.g., info, warn, error. The FSM could be in a state corresponding to the type of the last seen line, and this state information, e.g., creative idea, but using a Moore machine directly as the core optimization algorithm for hyperparameter tuning is generally not a practical or suitable approach. Here's why. 1. Nature of hyperparameter space. Hyperparameter tuning involves searching a space that is often high-dimensional, can include continuous values like learning rate, and is vast. Moore machines operate on a finite, predefined set of discrete states. it's very difficult to meaningfully map a complex hyperparameter space onto a finite set of states. 2. Output mechanism mismatch. In a Moore machine, the output depends only on the current state. In hyperparameter tuning, the crucial step is deciding the next set of hyperparameters to try based on the results, e.g., validation performance, of the previous sets. A Moore machine's output, determined solely by the current state, isn't naturally suited to generate a new, potentially complex hyperparameter configuration based on past performance feedback. The decision logic is missing. 3. Lack of adaptive learning. Effective hyperparameter tuning algorithms, like Bayesian optimization, evolution.
Okay. And state version of Moore machine, which would be more suitable comparable Come on, Gemini. Are you biased for LLMs? So there we have it. We are reaching RNN.
That's a great question.
So the question is there a continuous infinite state version of Moore machine which would be more suitable, adaptable, comparable for LLM tasks? Let's hear the answer.
Gets to the heart of why simple FSMs like Moore machines aren't sufficient for complex tasks like those handled by LLMs. While there isn't a formal model in classical automata theory typically called a continuous infinite state Moore machine, the concept you're describing aligns very closely with recurrent neural networks, RNNs. Here's why RNNs can be seen as fulfilling that conceptual role. 1. Sequential processing. Like Moore machines, RNNs process input data one step or token at a time in sequence. 2. Internal state, memory. RNNs maintain an internal hidden state. This state is a vector of numbers that gets updated at each time step. It serves as a memory, summarizing information from previous steps in the sequence, similar to how an FSM's current state summarizes relevant past inputs. 3. Continuous state space. This is the key difference. Unlike the finite, discrete states of a Moore machine, the hidden state vector of an RNN exists in a high-dimensional continuous space, defined by the real-valued activations of its neurons. Because the values are continuous, the number of possible states is effectively infinite. 4. Learned transitions. In an FSM, state transitions are defined by fixed rules. In an RNN, the function that updates the hidden state based on the current input and the previous hidden state is learned from data during training. These transitions are complex, nonlinear functions. 5. Output based on state. Like a Moore machine, the output of an RNN at a given time step can be determined primarily by its hidden state at that time step. Though variations exist where output also depends directly on the current input, more like a Mealy machine. RNNs as a bridge. RNNs, and their more advanced variants like LSTMs and GRUs, which better handle long sequences, were the dominant architecture for complex sequence modeling tasks, including natural language processing, before the rise of transformer models, which underpin most modern LLMs like GPT-4 or Claude 3. They are significantly more powerful than FSMs because their continuous, high-dimensional state space allows them to capture much more complex patterns and longer-range dependencies in data. Research has explicitly explored the relationship between RNNs and FSMs, showing how RNNs can simulate FSMs and how, sometimes, finite automata structures can be extracted from trained RNNs, compared to modern LLMs, transformers. While RNNs fit the description of a continuous infinite state sequential processor, most state-of-the-art LLMs today use the transformer architecture. Transformers move away from the strictly sequential state update of RNNs. They use attention mechanisms that allow the model to directly look at and weigh the importance of different parts of the entire input sequence when processing each part, rather than relying solely on a compressed hidden state passed step by step. This generally allows transformers to handle very long-range dependencies more effectively than RNNs.
Peace.